Okay, we're going to move to the next chapter, which is 17. Should be electrochemistry, as we finished 16 last time. This is also sort of the experiment we're going to be starting this week. And the first part of this lecture, or this chapter, we're going to go over redox reactions, how to balance them, oxidation states, how to assign them, and stuff like that. Again, just to make sure everybody is on that same page. Again, depending maybe on your Chem 50 instructor, maybe you went over some of that stuff, maybe you didn't really go over it all that much. And then later on today, probably we'll get into really the heart of sort of the chapter and what it's about. So let's get into it. Electrochemistry really deals with redox reactions. And redox reactions basically are oxidation and reduction reactions. And they are really, excuse me, they are really a big class of reactions that really deal with, in most cases, electrons being transferred. As you might remember, there's really three reasons why a reaction takes place. Basically, electron being transferred is one of them. The formation of a solid, or a formation of water. So redox reactions underneath that big umbrella fall basically more specific classifications of reactions, like synthesis reactions, decomposition reactions, single replacement reactions, combustion reactions. So those more sort of specific classifications do all fall under basically the redox reaction. And ultimately what's happening is electrons are sort of being transferred. So they always occur sort of together. So oxidation and reduction always happens basically at the same time. So a couple of definitions, as we will see here, in terms of oxidation and reduction, is oxidation basically means that something has lost electrons, and reduction means that something has gained electrons. So sometimes people remember that with Leo the lion goes grr. Loss of electrons, oxidation, gaining electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. You could choose both of them together. You don't have to pick, I suppose. But Leo the lion on the oil rig, he'll go grr, I imagine. There's some other definitions of oxidation and reduction which don't really relate too much to in a lot of sense, sort of what we deal with in here mostly. But there are definitions that you see a lot with organic chemistry when you're dealing with nonmetals. So a couple other definitions of each of these things. When we talk about oxidation, it can also mean the gaining of oxygen as you go from reactants to products, or the loss of hydrogen as you go from reactants to products. And reduction, sort of the obviously opposite definition here. It could also mean that you have lost oxygen as you go from reactants to products. And reduction could also mean that you gained hydrogen as you go from reactants to products. I would say probably in most cases, you're going to see those sort of definitions more so for organic chemistry when you're dealing with nonmetals. Most of the time here in sort of general chemistry, we deal with sort of the loss and gaining of electrons as sort of our definition of oxidation or reduction. But basically, each of those have three sort of definitions. But obviously, like as I mentioned, we'll probably be mainly focusing on the electron sort of definition. Any questions on that there? So in an electrochemical process, electrons are obviously transferred. And as we'll talk about, the sort of release of those electrons can be used to do some type of work. And here is an example of a reaction. This is a synthesis reaction. There's also really a combustion reaction. But we can look at this and sort of really figure out sort of what's going on in terms of everybody. And one way that we could sort of follow oxidation and reduction is to look at the oxidation states or numbers of things. So typically speaking, anything in a standard state that is uncombined will have an oxidation state of 0. An oxidation state is a little bit different than the charge we sort of associate with certain things in ionic compounds. And we'll talk a little bit more about that in just a second. But so in this case, magnesium and oxygen will have really no charge in the situation. Things really only get charges when really metals and nonmetals come together. And that's what happens on this side. Makes an ionic compound, and we have a +2 and a -2 sort of happening here for our oxygen. So when we're trying to decide what is being oxidized and what is being reduced, you really want to kind of look at sort of the oxidation states. And there's really a pretty simple way that you can, if you are able to identify oxidation states or numbers of things on each side of the arrow, that you can figure out what is being oxidized and what is being reduced by basically just using a simple number line. And usually to the right, there are positive numbers, to the left are negative numbers. And if we think about sort of the definition of oxidation, that means that you have lost electrons. And if you lose electrons, will you become more positive or negative? Yeah, you become more positive. So if you look at the oxidation number of something and it's sort of moving on the number line in the positive direction, that means that that substance is basically going through oxidation. And vice versa. Obviously, if you gain electrons through a reduction, you're going to now have more electrons than protons, and you're going to become more negative. So if you're on the number line here and you're kind of moving in the negative direction, that substance there is going to go through reduction. So if we just simply look at our example here, we have magnesium that started at 0 on the right-hand side, ended at +2. So it definitely is moving in the positive direction here. And that would mean that the magnesium here is being oxidized. By default as well, one of the nice things about redox is if you can figure out one thing, by default, the other guy's doing the opposite. So we know that really the oxygen here is being reduced. But we could also do the same thing for the oxygen. Oxygen started at 0 and ends at -2, which means it is moving, obviously, in the negative direction as well. So we could take this reaction here and we see that the magnesium is really sending those electrons over to the oxygen. And we can write two half reactions for this reaction that's taking place. And half reactions basically show the oxidation reaction that's taking place and also the reduction reaction that is taking place. And here we have our magnesium making a magnesium with a +2 charge and losing 4 electrons, and that is our oxidation half reaction. By the way, when it's the oxidation half reaction, the electrons should always find themselves on the product side. So electrons should be on the product side. And the oxygen is going to pick up those 4 electrons and going to form our oxide ion there. And again, electrons on the reactant side is definitely a example of a reduction reaction. So the side that the electrons are on also kind of helps you determine what is happening in terms of being oxidized or reduced. It is 4 electrons total because each magnesium is losing 2 electrons. So there's 2 of them. So obviously that's a total of 4 electrons. Also really important, these are called half reactions because frankly, when you add them back together, the electrons will cancel and you'll get back to the original reaction on the other side. That is also a really important thing when you have half reactions for a reaction like this. And you want to always make sure that the number of electrons in each half reaction are the same. And that's always what you want to do before you add those reactions back together. So we have an oxidation half reaction, we have a reduction half reaction, and obviously they're called half reactions because it's half of what's going on. And when you put them together to get the whole reaction, the electrons should always completely cancel out because however many electrons somebody loses should be the exact same number of electrons somebody gains. And that does require you sometimes in certain situations that you may have to multiply a half reaction by a number to get everybody to the same electrons. You may even have to multiply both half reactions by a number to get the electrons to be equal in both half reactions. So sometimes you do have to sort of manipulate the half reactions, but you always want to make sure in these sort of basic pretty simple redox equations that the electrons are always the same before you come and add them back together. Any questions on that there? By the way, this is what we should expect to happen in this case, right? Because magnesium is a metal, right? And oxygen is a non-metal. And it's usually the metals that should lose the electrons, right? And the non-metals should gain the electrons. So whenever you have an ionic compound like what we have here, that should be what you expect. So that's a good way to check yourself. So again, by adding these back together, as you can see there, we will cancel them out. Another thing that we sometimes also talk about is the oxidizing agent and the reducing agent. And the oxidizing agent and the reducing agent are different questions than what is being oxidized and what is being reduced. And what I mean by that is the substance that gets reduced is the oxidizing agent. And the reducing agent is the substance that gets oxidized. And once again, the reason they are called that is because that is essentially what they cause in the other thing. So in our example here, our magnesium gets oxidized, which means the magnesium here is our reducing agent. The oxygen gets reduced, which means the oxygen here is our oxidizing agent. So the reducing agent, which is the magnesium, will lose electrons because it's being oxidized. And because it loses electrons, that allows somebody else to gain those electrons and be reduced. So that is, again, the definition of it. The oxygen here will need to gain the electrons, which means it has to cause somebody else to lose electrons so that it can gain it. So that is why it is called the oxidizing agent. So the oxidizing agent, reducing agent, pretty much opposite of their names. And again, not to be confused when you're asked a question of what is being oxidized and what is being reduced. So again, those are two separate questions. But the answer to both of those questions should always be found on the reactant side. Yeah. So the oxidizing agent, the reducing agent, the thing being oxidized, the thing being reduced should always be found there on the reactant side. Any questions on that there? Here's another example here when we look at our calcium oxide being formed. And in this particular case, we have our calcium, which has an oxidation state of 0. We have our oxygen, which is uncombined, once again, has an oxidation state of 0. When those two come together, that is when the calcium gets a +2 charge, the oxygen gets a -2, really oxidation state. And once again, if you're not sure, you can just go this way. And if we look at the calcium, it starts at 0 and ends at +2, which means it's becoming more positive. So it is going through oxidation. The oxygen is starting at 0, and much like the last one there, is becoming -2, becoming more negative. So it is going through reduction. So in this case, once again, as we would expect in this case, because that is a metal, the calcium is being oxidized, the oxygen is being reduced. And once again, that means the calcium is our reducing agent, and the oxygen here is our oxidizing agent. So if we split it up into our two half reactions, this would be our oxidation half reaction, as the electrons there are on the product side, and once again, our reduction half reaction as they are being gained. As we can see here, electrons are 4 on each side. You could think of the arrows like an equal sign. So anything that is the same on opposite sides of the arrow can cancel down, kind of like you're subtracting it off. It could either completely cancel or reduce down as you're doing it. And we get obviously our overall reaction here. So again, as I mentioned, reducing agents are the guys that get oxidized. Our oxidizing agents are the guys that get reduced. Once again, if we had something like iron 3+, for example, going to iron 2+, is that being oxidized or reduced?
Reduced.
It is. So this is also where the number line can be helpful. May not be as obvious, as they're both obviously non-metals in this, or metals in this case, So if we look at it, we're starting at +3, which is like over here, and we're ending at +2, which means it is moving in the negative direction, and it is going through reduction. So again, that number line can be kind of helpful for things that may not be as obvious, as everything that we see will not always be kind of a metal and a non-metal together. So also very helpful when we look at really non-metals and non-metals together. As I mentioned earlier, and again, we probably won't see too much of this in here, but you definitely do see it in organic chemistry, and it's sort of the basis of when you think about different types of reactions, is those other definitions of oxidation again and reduction. And just a reminder, as I mentioned earlier, again, we can be gaining oxygen as we go from reactants to products here, losing hydrogen from reactants to products, and basically reduction is the opposite there, losing oxygen, which go from reactants to products, and gaining hydrogen. So if we look at this one, where maybe it may not be obvious to look at oxidation states, or there's no metals involved, but you just want to kind of see what's going on. If we look at the carbon, for example, from left to right, it definitely has gained electrons, which means the carbon here is being oxidized. You could also look at the tin. The tin here lost oxygen, which means it is being reduced. All right. And that would mean in this case, the carbon is our reducing agent, as it says there, and our tin with the +4 charge there would actually be our oxidizing agent here. So that would be our oxidizing agent in this particular case. So you can look at the gaining or losing of oxygen, hydrogen as you go from left to right. But again, probably most of the time here, you can just look at our oxidation states. But when you do see organic chemistry later on in your career, that's definitely the definition of oxidation and reduction that you see. In this particular case, we actually do have a metal here, so we can actually just look at the tin and see what's happening with the tin. The oxygen here, right, when we look at something like SnO2, oxygen is a -2 charge. There's 2 of them, which means that's a +4. And on the other side, we have tin that has basically no charge as it's by itself. So once again, if you just looked at the tin started at +4 and ended at 0, which means it is going through reduction, as we have imagined as well. So if you were able to figure out the tin part of it, again, by default, it would mean that the carbon in this case would have to be the one being oxidized. So again, there's sometimes multiple ways you can sort of figure out what is going on in terms of oxidation or reduction. Any questions on that there? So what really does help us figure out what is being oxidized and what is being reduced is looking at the oxidation number, or what is sometimes referred to as the oxidation state of a substance. The oxidation number, our state, is the charge that the atom would have if the electrons were completely transferred. So sometimes people are thrown off by oxidation numbers or states because you can have an oxidation number or state that is very different than the charges we normally associate with certain elements when they are in the ionic compound. So in an ionic compound, a particular element will either gain or lose electrons. So the charge that we associate with it is what we think about when we do naming and all that kind of stuff. And that's when we say something like things in group, 6 have a -2 charge, things in group 1 have a -1 charge, and so forth. So in an ionic compound, pretty much the oxidation state will be the charges that it will have. Now, in a covalent compound where we have sharing of electrons, we actually can get oxidation states or numbers that are very, very different than what we associate with the charges. So for example, bromine or chlorine that we normally associate as being -1 in an ionic compound, when they are sharing electrons, could actually end up with positive oxidation states. And that's a result of how they're sharing electrons, who they're sharing electrons with in terms of their electronegativity. So it could actually make them have a more positive oxidation state. So definitely when you get into sort of molecular compounds, covalent compounds, sharing of electrons, the oxidation numbers or state are going to be different than what we see in an ionic compound, where we do get that complete transfer of electrons. So let's talk about the rules for sort of assigning oxidation states. The first one is what we've just been talking about a little bit in some of those examples. Pretty much anything that is by itself, that's uncombined, kind of naturally how it comes, will have an oxidation state of 0. So those are things like H2O2, even though they are molecules, that is naturally how hydrogen and oxygen come. So they will have it. Remember that anything from the periodic table, by the way, does not have a charge unless it hooks up with somebody else, right? So if you have a piece of sodium metal or potassium metal, it doesn't have a charge and it has a 0 oxidation state. Things that are monoatomic ions and things sort of in their ionic sort of formula or compound will have basically the same charge as you would expect. So the oxidation state would be the charge. So if you had iron 2 chloride, that's -1, and that would be a +2. So the iron would have a +2 oxidation state, just like it would have a +2 charge, obviously, in that situation. That again is an ionic compound where we would expect electrons to be transferred. I would say when you're assigning oxidation states or numbers, a lot of times oxygen's involved. So that's a really good place to start assigning your oxidation numbers. So oxygen typically will have a -2 oxidation state. There is an exception though, and that exception is if it really is not necessarily oxygen by itself, but that it is peroxide, like in hydrogen peroxide, sodium peroxide. Then in that case, the oxygen will have a -1 oxidation state. I would say probably in most cases, 9 times out of 10, if you see oxygen, it's probably oxygen. So it probably will have that -2 charge, but it could be peroxide. Again, typically the way you can recognize peroxide is, you got those extra couple of 2s in the formula, like you see here, H2O2, then you kind of know it's peroxide. But if it is peroxide, then it'll be -1. Hydrogen will have a oxidation state of +1 unless it comes after a metal like LiH. In that case, it is -1 in that case, right? +1, -1. So if it comes after a metal, hydrogen will be -1. Other than that, you could assume that hydrogen is going to be +1. Group 1 metals will always be +1. Group 2 will be +2, and fluorine is always -1. Now, the sum of the oxidation numbers, when you add them all together, all the oxidation numbers do have to equal the charge that may be on that molecule or ion. And if it's a molecule, it probably will have a neutral charge, which means they all should add up to 0. If it is an ion that you're trying to sort of establish the oxidation number, then it should add up to the charge of the ion. So if the overall charge is -1, when you add up all the oxidation numbers, you should be left with a -1. So if we look at something like bicarbonate, and when you got kind of like a 3-pack happening here of elements, and you got oxygen, and once again, that's a good place to start. And you would start with the oxygen there and go with -2. There are 3 of them, which gives you a -6 kind of overall happening. In this case, when you do have 3 in a row like this, usually you want to go right, left, and save the guy in the middle for the end is usually a good move. So we'll go to the left there. That's hydrogen. That's +1. Once again, in this case, it does need to add up to the overall charge of bicarbonate, which is -1 in this case. So that's a lot of math for this early morning, but we'll go with +4 perhaps. There will get us there. So that's going to get us an oxidation state of carbon of +4. So when we look at this and you're asked to give the oxidation number or the oxidation state, the correct answer here for each of these is hydrogen is +1, carbon is +4, and oxygen is -2. So we're not looking for the grand total of everybody that's there. So when you are stating the oxidation state or number, you should give it for obviously one of the elements by itself, what it is, not the grand total. You should also, as I did there, include the charges, even on things that are positive, yes, because it's not implied that it is positive too. because it could be -2. So you do need to include the positives and the negatives when you're assigning oxidation numbers and states and you're writing them so that there is no misunderstanding. Any questions on that there? All right, so why don't you take a few moments here and assign the oxidation numbers for each of these guys. Okay, let's take a look. So first off here, we got a little Li and 2O. So this is lithium oxide, so it's really an ionic compound, which means pretty much the oxidation states will be the charges. So oxygen here should be -2, and the lithium here should be +1 in this case, like we would expect, as that's a group 1. Once again, for lithium, it is +1, not +2, the total sort of overall sort of charge that you got going on there. For PF3, we would start with our fluorine here, which is -1, as it should always be. That's going to give us a -3. This means that phosphorus in this case actually is going to be +3 to balance it out to 0, as there's no charge in there. So phosphorus would be +3. Fluorine here would be -1. Any questions on that? So again, this is an example of, in this case, we have phosphorus and fluorine, which are two nonmetals sharing electrons in this case. And in this case, if we just gonna sketched it up, probably maybe something like this. I don't know, something like that. So in this case, 21, 26, that looks about right. We have fluorine, which is way more electronegative, right? So it's going to pull those electrons, because they are sharing, away from the phosphorus, right? And that's going to make the phosphorus more and more electron deficient and more a positive charge. And that's a very different outcome than what you have in an ionic compound, where phosphorus is actually the recipient of the electrons coming in. And that's why we associate phosphorus normally as -3 in an ionic compound, because it's gaining those electrons from the metal in that situation. But in this situation, it's actually the one that's going to be kind of like losing its electrons towards the more electronegative fluorine, because they're sharing electrons. So definitely going to be shared unequally in this case. Question on that there. Here we have a little HNO3, some nitric acid. So once again, I'm going to start with the oxygen, which is -2. That's going to give me a -6. And our hydrogen here would be +1. This is going to equal 0. So in this case, our nitrogen is going to have a +5 oxidation state. So hydrogen here would be +1. Nitrogen would be +5. And once again, for oxygen, it would be -2 in this case. Any questions on that one there? So here, a little dichromate action. Oxygen, once again, going to be -2, and there's 7 of them. That gives us like a -14. Overall, this is going to have a -2 charge. There's actually not one chromium here, but there are 2. So you could do like a little math problem if you like. That means that in this case, each of the chromiums are going to be +6. That will give us a 12 minus 14 equals -2, basically, when it's all said and done. So the chromium here going to be +6. The oxygen going to be -2 in this case. Any questions on how to assign oxidation states correctly? So again, these illustrate the idea that when things do share electrons in a covalent situation, because of who they're sharing electrons with and the difference in electronegativity of those elements, it can cause elements that we normally associate with negative charges to actually become more of a positive oxidation state. I think we saw something similar to that when we were looking at acid strength. So we had like, something like this, where we actually had the hydrogen. But in this situation here, oxygen -2, -2, -2. In this particular case, if this was -1 overall, the chlorine would be +5, as that's ClO3 minus chlorate, basically. As opposed to if we just had ClO minus, which would look something like this, basically, -2, and in this case, +2. So in the case here of chlorate, with those 3 oxygens kind of pulling the electrons away from the chlorine, making it more and more positive, versus just the 1 oxygen in this case, still making it more positive, then we associate with it at being a negative charge when it receives the electrons in an ionic compound. But again, because of the sharing electrons, difference in electronegativity, and what elements they're sharing in these molecular covalent compounds, this is why we end up with positive oxidation numbers or states for certain elements, again, that we associate sometimes as negative. Any questions on oxidation numbers or anything like that? All right. So the next thing we're going to talk about is balancing redox reactions. So when we balance redox reactions, there's kind of 2 types. There's kind of like what we saw at the very beginning here, which I would term as sort of basic sort of redox reactions. And when you have some basic redox reactions, all you have to do pretty much is, like we talked about, make sure that the electrons in each half reaction are the same. Then you add them together and the electrons should cancel out. When we start balancing redox reactions in acidic or basic conditions, it gets a little bit more involved in terms of how you go about balancing redox reactions. So we're going to go through the steps of how to balance it in acidic conditions, also basic conditions, and then you should hopefully be good, I hope. All right, so just to make sure everybody has done this before or not, we'll make sure we all do it here together. So we're going to look at this one here, and we're going to start with doing it in acidic conditions. So we have iron 2 going to iron 3. We have some dichromate going to chromium 3. I would say probably the first thing that you really want to do when you have a reaction like this is sort of really figure out what is going on. And by that, you should really start assigning some oxidation numbers and try to determine what is being oxidized and what is being reduced. So in this particular case, we will start with the iron 2. So clearly the iron 2 has a +2 oxidation state. We just did this guy a second ago. So our oxygen is -2. Our chromium here was +6. On the right-hand side here, our iron is +3 and our chromium is also +3. So if you are not sure what's going on, we again could kind of go to the little number line action. And if we look at the iron is starting at +2, which is like there. And it's ending at +3, which means the iron is moving in a more positive direction. And that means in this case that the iron should be oxidized, right? As it's becoming more positive. By the way, by default, as soon as I determine that, I already know that this guy should be the guy that is being reduced. We could still do it for the chromium. Chromium on the left-hand side there is +6, which is like over here. And it ends on the right-hand side at +3, which means it is moving in a more negative direction and is being reduced. That would also mean in this case that my iron is going to be my reducing agent, right? The iron with the +2 charge. And my chromium here actually will be my oxidizing agent. First off, any questions on assigning those oxidation states or determining who's being oxidized, who's being reduced? All right, so now that we have that set in our head, and why it's important to really kind of do that is it can help you double check that you didn't screw up along the way, yeah, which can happen. So it can sort of help you make sure, that maybe you won't mess up the longer process here. Once you have sort of who's being oxidized, who's being reduced, the next thing that you want to do is take that reaction and basically split it up into its 2 half reactions. So you should have a oxidation half reaction, you should have a reduction half reaction. And to split them up into the half reactions, you just simply take the same elements, one on each side, and put them together basically. So obviously I have an iron with a +2 on the left, and that should probably be paired up with the iron with a +3 on the right, since they're the same element. I also have a chromium on the left in the form of Cr2O7 2-, which is our dichromate. And obviously I have a chromium on the right, which should be paired up. Now, by determining what we had going on here, we know that this is our oxidation half reaction. That is our reduction half reaction that's happening. Once you split it off into its half reactions, the next thing that you want to do is balance all the elements except for hydrogen and oxygen. So you want to balance all the elements. So basically you want to balance all elements besides hydrogen and oxygen. And the way that we balance it is just like a normal equation. We're just going to add a coefficient to do so. And the purpose of all this, by the way, when we're all done and we have this equation that is completely balanced, it needs to really be balanced in two ways. It needs to be balanced like a normal chemical reaction or equation, that you have the same number of elements on both sides of the arrow. And it also has to be balanced in terms of overall charge on the left-hand side of the arrow, and the right-hand side of the arrow needs to be balanced. So when we do these, we actually have to look at two things when we're all done to make sure that those are completed. In this particular case, we have one iron on the left and one on the right. Although they have different charges, there's still just one iron on the left and one on the right. But we do need to put a 2 here in front of our chromium to balance out the chromium at this point. Once you've balanced out everything except for hydrogen and oxygen, the next thing that you want to do is balance out the oxygen. And the way that we balance out oxygens in this process is we add water. And we add water to whatever side needs oxygen. Now, the problem with adding water is, although it will balance out the oxygens, every time I add water, I'm also adding what other element? Hydrogen, yeah. So every time that I add water to one side, I have to then add 2 H pluses to the other side. So we do add water to whichever side needs the oxygen, but to keep everything balanced, we then would want to add H plus to the other side, 2 H pluses for every water that we add. By the way, if you happen to have started a half reaction like we have here, we don't actually have an example of it here, but in these half reactions, if you happen to have a half reaction where you are initially starting with like an extra hydrogen on one side versus the other, you could just add an H plus to the opposite side up front to balance it out. So sometimes that happens. For example, you just say we had NO3 minus and we had like HNO2 or something like that to start with. You can just right off the bat add the H plus to the other side to balance out that hydrogen. At some point you'll need to add that hydrogen, otherwise you'll be short along the way. So sometimes it happens when you break it off into the half reactions, you have sort of an unequal number of hydrogens. To take care of it up front is probably a good idea as well. Now that we have everything balanced, we're going to add our oxygens. In this case, the iron half reaction has no oxygen, so you don't need to add water. The guy on the bottom has 7 oxygens on the left, which means to the right-hand side here, we would need to add 7 waters to balance that out. Because we added 7 waters to the right-hand side, to the left-hand side, we would need to add 14 hydrogens. And that's basically from here to make sure that we have the right number of hydrogens happening. Any questions on that so far? At this point, you really should have kind of everything balanced in terms of elements. Hydrogen and oxygen as well balanced. Again, if you happen to have an extra hydrogen, then at this point you should add some extra H plus to the opposite side. The next thing that we want to do in this balancing process is, once we've done all that, we want to balance the overall charge on each side of the arrows in each half reaction. So we want to balance the charge, and we're going to do that by adding electrons. So we're going to add some negative electrons to whichever side needs them to balance out the overall charge. Now, I personally think that the easiest way to do this is to frankly look at the overall charge on each side and not go element by element. Sometimes people are taught like go element by element. That's a waste of time, because what we just learned when we talked about oxidation numbers and states is, if I look at something like Cr2O7 minus, when I add up all the oxidation states for that guy, it should equal -2. So why reinvent the wheel? Yeah, it's already done for you. So you don't have to then go, okay, like, is that guy losing 2 electrons or, and all that kind of stuff. So just look at the overall charge on each side. By the way, it does not have to equal 0 on both sides. It just needs to equal the same number on both sides of the arrow. So it doesn't have to equal 0. So if we look on the left-hand side here, the first over here, we have a +3 working. So we are adding negative electrons. So the side that needs the electrons should be the right-hand side here. And we would need 1 electron there. That would give us a -1, which would totals out to +2 on the right to match the +2 there on the left. Any questions on that there? Doing the same approach for the bottom. Again, I'm just going to look at what we got going on in terms of the overall charge. That is a +14. This entire thing is a -2, which gives me like a +12 happening there on the left. That is a +6 as we take 2 times 3, and that is neutral, which is a 0. So we got +6 on the right. We have +12 on the left. That means, bless you, that the left-hand side here would need 6 electrons, and that would give us a -6, and a +12 gives us a +6 left over on both sides. Any questions on how to add those electrons? By the way, here I added some electrons. The purpose of figuring out what is being oxidized and what is being reduced is, at this point, you can make sure that you did put the electrons on the correct side. I threw some electrons over here on the product side, and that's good because that is my oxidation half reaction. So if I ended up with electrons on the left-hand side, that would not be so good. Something not right with your math. Over here, I threw some electrons on the left-hand side, which is our reactant side, and that's good because that is a reduction half reaction. The electrons should never, ever be added to the same side because they should always be canceling out, because ultimately what's happening is they are being transferred from one to the next, which means they can never be on the same side. So these are things that you want to think about as you're doing this to make sure, you know, that it makes sense of what is going on. Any questions on that there? All right. So now that we have electrons, I'm just going to clean up some of my scribble here. I think we'll finish out here. So I'll get rid of all this stuff here. Okay. So now that we have the electrons, we're pretty close to the part where we want to add both of these back together. But as I mentioned before we could add them back together, we do have to make sure we have the same number of electrons. And in this case, we do not. So we do need to multiply, in this case, everybody by 6. And that's just for the iron half reaction in this case. And that will give us, hopefully, our 6 electrons that we need in each of these cases. So if we do that, I'm just going to recopy below it that 6. So 6 iron 2 go to 6 of the iron 3 plus our 6 electrons. So at this point, we are now ready to add these together. Once again, anything that's on opposite sides of the arrow can reduce or cancel out. So for sure, though, our electrons should always completely cancel. And I think in this case, that is it in terms of what is happening. So we will have 14 hydrogens, and everybody on the left-hand side of the arrow stays there, plus some dichromate, plus 6 of the iron 2. Everybody on the right-hand side of the arrow will stay there as well. So 2 of the Cr3 plus 7 waters, and 6 of the iron 3 in this case. Now, if I have successfully done this correctly, this should be my balanced equation in acidic conditions. How do I know if I did this correctly? As I mentioned before, it should be balanced 2 ways, just like a normal equation, which means I should have the same number of elements on each side. So if we take a look at it quickly here, I got 14 hydrogens there, 14 there, so that's good. I got 2 Crs there, 2 there, so that's good. I got 7 oxygens there. I got 7 there, so that's good. I got 6 irons and 6 irons, so that is balanced. Overall charge happening on the left-hand side is this guy's going to contribute plus 14. This guy will contribute minus 2, and this guy will contribute plus 12. And if I'm not mistaken, that is 0 when it's all said and done, I hope. Unless I did some bad math there, which I maybe did, but that is not 0. That is going to be plus 24. That's a better math, I suppose, as well. I'll whip out the calculator shortly. It'll be all right. So on the right-hand side here, that is plus 6. That guy is 0, and this guy is plus 18. So 18 and 6 is better math of 24, I think. Yeah, so we have plus 24 on each side. Should have got the calculator. I know, it's all right. Any questions on how to balance it in acidic conditions?
What makes this?
What makes it acidic?
Yeah.
What do we see on the left-hand side of the arrow? What's there? Yeah, H plus. That's how you know it's actually balanced in acidic conditions, because you do see H plus. Yeah.
Like when we start.
How do you, is your question? How do you know in the question if it's acidic? It usually.
Acidic versus basic.
So it will tell you, if your question is, it will usually tell you that it's acidic. Are you doing something in some type of acidic conditions? Like, for example, the experiment we're going to do, at some point you're going to add some acid to your reaction, right? So clearly that's going to be acidic conditions, and you would want to balance it. Just like we will add some base to the reaction as you go through there, a couple of drops of sodium hydroxide or HCl. So that will tell you, if you're doing some type of experiment, what type of conditions you do it. Usually in textbook problems or something like that, they will just simply say a balance in acidic conditions, or they'll put in parentheses at the end, acidic or basic, and that's how you know it. Otherwise, you may actually see sometimes people even in this original sort of problem or equation, they'll put like H plus on one side or OH minus in there, and that'll also give you an idea that it's acidic or basic.
The balancing doesn't change whether or not it's basic.
It does. So we're going to talk about basic right now. So it does change, or you do have to do something if it is basic versus acidic. So this, what we just talked about, is acidic conditions. And the reason we're going to go through acidic conditions here first is I personally think that it is easier to balance basic conditions by just doing it acidic first. And then at the end, you could change it into a basic type of deal. Now, to do basic conditions, that would be my recommendation, to just balance it like it's acidic. And at the end here, we could turn this guy into a basic conditions very simply. You could also do basic conditions a little bit earlier on in the process, where before you add the electrons, you could add some hydroxide up front in there. But it does require at that point a lot of like canceling and stuff and combining. So the cleanest way to probably do it is just to balance the equation in acidic conditions and then turn it into basic. So let's talk about how to do that. So if we were going to do this one now, say in basic conditions, I would do just as I mentioned, pretty much everything we just did to get to the acidic conditions. And where I would pick it up is at the end here with our balanced equation in acidic conditions. So I grab some room here. So now that I have balanced it in acidic conditions, all you need to do is actually take the equation that you just wrote. So I'm just going to recopy it above. So this is our balanced equation here. Maybe if it writes, I will write it. Try it again. There we go. So this is our balanced equation in acidic conditions. All right, so to turn this into basic conditions, here's what you need to do. You need to add OH minus to both sides. And the amount of OH minus that you're going to add is going to be equal to the number of H pluses you have. So once again, you just roll through the entire acidic process. You end up with your balanced acidic equation. And at this point, you're going to add OH minus to both sides. And it's going to be equal to the number of H pluses that we have. So in this particular example, we have 14 H pluses. So that means what we would do is add 14 OH minuses once again to both sides, not just one side, but both sides. Now, when we do this and you do this process, there's going to be a point where you have H plus and OH minus, and H plus and OH minus come together to make water. So that will give you 14 waters. And usually what will also happen at this point is you'll have some waters on the other side. So you could do some reducing down of waters. So we have 7 waters on the right. We'll now make my 14 waters 7 on the left. And now everything else stays the same. And if we did that all correctly, just like that, we now have it in basic conditions balanced. Yeah. And it should still be balanced both ways. So once again, if we take a look, I got 14 hydrogens there, 14 over here. I got 7 oxygens there, and 7 more is 14. So 14 oxygens. I got 2 CRs on the left, 2 on the right, 6 irons on the left, 6 on the right. Overall charge, this water on the left is 0. That's -2, and that is +12. I'm going to try better this time. That's a +10. Hope for the best. On the right hand side, that's going to be a +6. That's a +18, and that is a -14 contribution. So that's going to give us a net +10. So we are still balanced. We once again, as earlier, know that this is balanced in basic conditions because what we see in the final reaction is OH minus. Yeah, so we know that this is basic conditions. It's been balanced. And obviously down here was acidic conditions. So that, I would say, is probably the easiest way to balance it in basic conditions, is really just to balance it in acidic conditions. And at the end, all you have to do is take however many H pluses you have, equal number of OH minus on each side, combine to make water, and usually reduce down the waters. As I mentioned before, you could do this process again before you add the electrons. You can add the OH minuses at that point. But in my experience, it sometimes confuses people because you get a lot of like waters and stuff in the middle, and you got to kind of reduce down. So it's just a little bit cleaner just to wait to the end to do it and flip it over to basic. So that's sort of how quickly you can kind of make it into a basic sort of deal. Any questions on that one there? Look, see how you're doing. So we're going to balance this guy in basic conditions. So again, I'm going to really try to figure out what is going on in terms of who's being oxidized, who's being reduced. So if we just take a look at that first and assign some oxidation numbers, I minus has an oxidation number of -1. Our MnO4 minus, that's going to be -2 for the oxygen. That's 8 of them. -8 overall, it needs to be -1. That means that the Mn in this case has a +7 oxidation state there to get us to our -1 overall. I2 is how it naturally comes, which means it has oxidation state of 0. Once again, looking at MnO2, that's going to be a -2, -4, needs to equal 0. So +4 in this particular case for the Mn. Once again, if you're not sure, you can go with the number line approach. And if we look at the I minus, starts at -1, ends at 0. So it is actually becoming more positive. So the I minus here is being oxidized. By default, that means this guy should be reduced. We could also, again, look at it on the number line. The Mn is starting at like +7 over here, and it is ending at +4, which means it is moving in a more negative direction and becoming reduced. That means in this case, that is my reducing agent. This would be my oxidizing agent. Any questions on any of that there? All right, so now that we got an idea of what's going on, we're going to separate out our 2 half reactions here. So just the guys that go together will stay together. So we got that, and we got some MnO4 action happening there. Next thing we're going to do is balance everything but oxygen and hydrogen. So in this case, we need to put a 2 there for our I. And other than that, I think we're good. Now we could go to oxygen by adding water. So the top one has no oxygen, so it does not need water. Bottom one, we got 4 oxygens on the left, 2 on the right. That means on the right-hand side there, we will need 2 waters to balance out the oxygens. That also means to the left-hand side, we need 4 H pluses. Yeah. Any questions on that there? We're balanced now with everything, so it's time to turn to electrons being added. So again, we want to look at overall charge. Left-hand side -2, right-hand side 0. So that's going to be a couple of electrons there on the right-hand side to get us to basically -2 on both. We know that this is our oxidation reaction, and that's our reduction. So that's good. We did put it hopefully on the correct side. We have a +4 here. Once again, a -1, 0, and 0. So dare I say that is +3. So we need 3 electrons there. I was almost going to say 5, but you know, I did it right there at the end. All right. So that obviously will give us -3 and gets us a net of 0 there on the left as well. Any questions so far? Now that we have our electrons properly placed, also in that last half reaction, we put our electrons on the left-hand side, and that is the reduction half reaction. So that's good. I'm just going to clean up some of the scribble here. At this point, we do need to add them together, but we cannot do so because we do have electrons that are not equal to each other. So common number between those two is just to multiply them together. That's 6. So top one needs to be multiplied by 3. And the entire bottom reaction there needs to be multiplied by 2 to get us to 6. I'm just going to recopy everything kind of underneath it here. So that's going to give me 6I minus goes to 3I2 plus 6 electrons on the bottom there. That's going to give me 6 electrons plus 8 H pluses plus 2 of the MnO4 minus, 2 of the MnO2, and 4 waters in this case. Now that we do have the same number of electrons, we're ready to add these together. Our electrons should cancel. And I think in this case, that is all that will cancel. So I will end up with 8 H pluses plus 2 MnO4 minus plus 6 iodide. That's everything on the left-hand side of the arrows. 3I2 plus 2 MnO2 and 4 waters in this case. And if I were to do it for acidic conditions, I technically would be done at this point. I could put a box around it and be done. I also would know it's acidic conditions because, again, I see H plus there on the left-hand side. Overall, it should still be balanced just to make sure. We got 8 hydrogens on each side, 2 Mns, 8 oxygens. So 4 and 4 is 8 on the right there, 6 iodides. And overall charge on the left is 0. Overall charge on the right is 0 as well. So again, good idea just to double check that it is balanced in acidic conditions before we go and turn this into basic. Yeah. Any questions up to that point? Yeah.
Going back to when you added water.
Yeah.
The reason why we're adding the water is because there's oxygen imbalance on the products.
Right. That's exactly right. So in this method, the way that we balance oxygen is to add water. But the process of adding water not only adds oxygen, but it does add hydrogens to the other side. So to balance it out so you're not short hydrogens at the end, to the opposite side of wherever you have the water, you have to add 2 H pluses for every water that you add. Other questions? All right, so to turn this into basic, as we talked about, all you pretty much need to do is just add an equal number of H pluses. And in this case, our H pluses is 8. So we're going to add 8 OH minuses to both sides here. Once again, on the side where you have H plus and OH minus, that's going to make 8 waters. And I can reduce down the waters in this case, as there's 4 on the right-hand side. So that's going to give me a net of 4 waters on the left, plus 2 MnO4 minus, plus 6 iodide, 3I2 plus 2 MnO2, and 8 OH minuses there. And once again here, I know it's basic because I still see the OH minus there. and it should still be balanced. So once again, we have 8 hydrogens on the left and right. We have 12 oxygens on the left, and we have 4 and 8 on the right, which is 12. 2 MNs on both sides and 6 iodides. Overall charge on the left now is actually -8 to match the -8 overall charge that we have on the right-hand side with the hydroxide there. So we are balanced. Yeah. Any questions on any of that? Yeah. How I got the 3 electrons? The down here? Yeah. Yeah. So before we did that, we had basically this, right? So what you're looking at is overall charge on each side. So this is contributing a +4 charge. That is contributing a -1 charge overall. And on the right-hand side, they're both neutral, which means basically on the right-hand side, everybody's 0. So we basically have on the left +3 and on the right 0. So by adding the 3 electrons to the left, that will give us 0 and 0 on both sides. Yeah. Awesome. Other questions? Yeah. Yeah. Yeah, so when you turn it into basic conditions, wherever you have H plus and OH minus, they have a really strong attraction for each other. They're going to want to make water. So that's why we originally ended up with 8 waters on the left. And because we also had 4 waters on the right, we're able to kind of reduce it down and subtract it over. Yeah. Other questions? All right, one last one here. We'll skip that one. We'll do this one. Why not? Let's try this one. That looks like a lot of fun C's in there. Little dichromate, little oxalate, little car. Okay, let's take a look, see how you're doing on this one here. So we're gonna figure out what's going on first. So we've done some of these oxidation numbers. So that was a +6 for that guy. Once again here, this is gonna be a -2. There's -8 needs to equal -2. There's 2 of them, so that's like a +3, I think, there for our copper. Not copper, carbon, whatever the element that is. I don't know. That's +6 there, gives us a -2. That's going to be a +3. -2 for the oxygen gives us a -4, so +4. So once again, if we look and see what's going on here for our chromium, starting at +6 and ending at +3, which means it is moving in a negative direction. So it is being reduced in this case. The carbon is starting at +3, which is like here. And it is ending at +4, which is moving in that direction, becoming more positive, which means it is being oxidized. That once again means that this guy is my oxidizing agent. This one here is my reducing agent. Any questions on any of that there? All right, so splitting it off here, chromium with chromium, carbon with carbon. And as we just established, that's our reduction half reaction, and this oxalate here will be our oxidation. So we're going to balance everything besides oxygen and hydrogen first. So we're going to need a layup. It looks like a 2 right about there. We also need to lay up a 2 there for the carbon, I believe. In this case, that means that we can now move to our water. We do need 7 waters on the right-hand side here to give us our 7 oxygens. That also means we will need 14 H pluses. By actually putting the 2 in front there, the CO2, we are now balanced. We don't need any waters there on the bottom as we have 4 oxygens on each side. So important to go in that order first. Yeah. Any questions on that there? At this point, we can go into electrons. So that is going to give us a +14. This is going to give us a -2, which gives us a net of +12. Right-hand side +6 and 0. So left-hand side here will need 6 electrons, as that then would get us a net of +6 there on both sides. Yeah. Any questions on that one there? Again, also makes sense since that's our reduction. We put it on the reactant side, so it all balances. Bottom one there, overall, we got a -2 and 0. So we do need 2 electrons there on the right-hand side in this particular case. And that will balance us out for that guy. Any questions on adding electrons or how I got 6? I can. Let me go back and replay that there. There we go. All right, so here we go. Instant replay. So this guy's going to contribute +14. This entire thing is a -2, right? That, if you take together, gives you a +12 happening there. Right-hand side, that's going to give us a +6, and this guy is 0, which gives you for the right-hand side there a +6. So remember, we need to balance it out. We'll need those 6 electrons there to get us a -6, and that gets us to a +6 on both sides. Yep, other questions? All right, so we're ready to add, except we don't have the same number of electrons. In this case, it looks like we just need to take care of the bottom one there. We're going to multiply it by 3. So I'm just going to recopy the top equation. So I have it. And also, if you do this, make sure you recopy it correctly, right? That would be good. And I'm then going to multiply the 3 to our bottom equation. And now I'm good to add. That's going to get rid of my electrons. And I think that's all I got. So again, everybody on the left-hand side of the arrow will stay there. So 14H pluses, a little Cr2O72 minus, plus 3C2O42 minus. Right-hand side, 2Cr3 plus, 7 waters, and 6 CO2s. And once again, at this point, that should be balanced in acidic conditions. We got 14 hydrogens there, 14 there, 7 oxygens there, and 12 more is a lot. That's 19. That is 12 oxygens there, plus 7 more is 19. 6 carbons. I cannot always get this confused. 6 carbons on that side, and 2 CRs on each side. Overall charge, we got +14 from this guy, -2, and -6. That's like a +6 overall, I think, happening. Right-hand side, +6, 0, and 0 gives us a +6 on both sides. So we're balanced. Once again, we know this is acidic because we do see the H plus there. Yeah. Any questions on how to balance these acidic or basic conditions? Yes. All right, so we'll lay that up for lecturing here.